It's pleasure to announce the speaker of our seminar today, Pedro Carvalho from University of Hradec Kralove. He is a new member of the University of Hradec Králové, and before that he just finished PhD in IMPA
Yes.
with the Professor Burstein.
Yes, exactly.
Please.
Yeah. Okay. So thank you for the invitation to speak at this seminar. So it's good for me to talk about my things finally to you. So okay. So how much time do I have? Like 50 minutes? Okay, great. So it's more than enough, I think. Okay, so today I want to talk about part of what I did for my PhD thesis at IMPA under the supervision of Professor Henrique Burstein. So it's about this homological reduction of Poisson structures. Well, let's see how it goes. Okay, so let me just start by giving you some context. So for us, I will be working here in the context of, well, reduction of Poisson structures, right? Reduction of Poisson manifolds. So consider, so a Poisson manifold, have a manifold with a Poisson bivector, and consider the usual data for doing Hamiltonian reduction. So we have a Lie algebra action and a moment map, okay? So in this context, there's something that I'm calling here BFV in degree 0. So, and, you know, in the literature, in this context here, there's something that is called Kostant-Sternberg BRST algebra. And this is like, it's a super Poisson algebra, differential graded super Poisson algebra, whose cohomology in degree 0 knows about the algebra functions of the reduced space associated to this reduction data. So you consider the constraints to manifold given by the moment map, and then you can quotient out by the action. You have a new Poisson manifold, and this BFV in degree 0 here you can see as some kind of, you know, some algebraic techniques that you apply to this reduction data. It constructs for you a certain algebraic object that knows about the algebra functions of the reduced space. So somehow algebraic version of the reduction. Okay, so you replace somehow the Poisson, the reduced Poisson manifold by this differential graded Poisson algebra. Okay, so what I want to do here today, my idea is to apply these BFV techniques or these BFV models or this homological reduction to Hamiltonian reduction, but of graded simplex manifolds. But I want to extract from these models for reduction of usual Poisson structures. So it's doing graded BFV, but with a view towards the usual Poisson reduction. Okay, so you can ask, okay, but why does it make sense? So there is a graded simplex viewpoint for Poisson manifolds. This is work, this has been known for some time. This is work by Roytenberg and Ševera. So there is a correspondence between Poisson manifolds and simplex NQ manifolds of degree 1. So in these simplex NQ manifolds of degree 1, they are simply shifted cotangent bundles. And this homological vector field is like just the vector field given by taking the adjoint action of with the Poisson bivector. So there's one-to-one correspondence between these objects.
So
okay.
What is degree 1?
The simplex structure is of degree 1.
This
Yeah, in this case here, like I wrote with the Poisson bracket, but in this case, the simplex structure is of degree 1, but the Poisson bracket is of degree -1. Okay, so I will talk about more about it later. And this has been done for some time, but what's kind of like the new, something that was later done, it's work by Professor Alberto Cattaneo and Professor Cattaneo-Zambon, is actually a relation between reduction of the graded structure and reduction of the Poisson structure. So on this side here, below here, I mean coisotropic and press-simplex reduction of the shifted cotangent bundle, but it's reduction of the graded structure. And there is a way of relating this to reduction of the Poisson structure itself. So I will talk more about it later as well. So it's really like extending this dictionary here to the level of reduction of the corresponding structures. Okay, so good. So, and as I said, I want to do this BFV in this graded context, looking for homological models for Poisson reduction. So I had this picture in mind that you can go back and forth with this graded reduction and Poisson reduction. Okay, so in particular, one particular case of this correspondence between graded reduction and Poisson reduction is what I'm calling here generalized Hamiltonian setting. It's also work by, it's in this paper by Cattaneo and Zambon. It's that if you look at Hamiltonian reduction of the shifted cotangent bundle, it's a specific coisotropic way of doing reduction there. So you have the Hamiltonian action of a graded Lie algebra. It's compatible in a suitable way with a bivector. I will explain what the compatibility are. But then you can translate this to the following non-graded, let's say, picture. You have a G action on the Poisson manifold. So you have a usual action. But now you have a equivariant map that is, the usual Hamiltonian context. The moment map takes value in the dual of the Lie algebra. And in this case here, the moment map takes values in the dual of a G module. So it's slightly more general. And when you translate the compatibility here, there's also some, the condition that the bivector satisfied with respect to this data here is also weaker in a certain sense. In particular, you don't need the bivector. One thing that appears in the usual Hamiltonian context is that the bivector is invariant by the action. And in this case, you don't need the bivector to be invariant. So it is slightly more general than the usual Hamiltonian setting. And in this paper by Cattaneo and Zambon, there is like some type of Marsden-Weinstein theorem for this, for doing reduction with respect to this data here. So in the usual Marsden-Weinstein theorem, we know that if you have like a Hamiltonian space, you can take the constraints to manifold given by the zero level set of the moment map, you quotient out, you have a new Poisson manifold, right? Upon some regularity conditions. And for this more general Hamiltonian setup, they also have Marsden-Weinstein theorem, so to speak, like in this generalized context. So if you know that when you do like this BFV, there's like this Kostant-Sternberg BRST algebra that gives you this differential graded Poisson algebra associated to reduction. Well, it's kind of natural to ask you it's kind of natural to ask what's the corresponding homological version of this thing here. So what should appear when you consider more general Poisson reduction setups? What should be the algebraic structure of the homological model of this type of thing? Okay.
So, should we be reading that theorem? Or should you read it for us?
Well, I just like it's just like it's just like considering if you consider the G action in the equivariant moment map. So you assume some regularity condition. I'm saying that assume that the pair. I will explain exactly what regular and compatible means. I will explain later. But it's just to say that you have some reduction, generalized reduction data, you have some compatibility. And I just wrote it here because I want to say that out of this you can produce some Poisson manifold. No, like it's the technical assumption is not really important like now, but it's just like you have some compatibility between this data and the Poisson structure, and you produce some manifold.
But if you just go back to Dirac, Kostant-Sternberg, so what makes this Cattaneo-Zambon compared to compared to reductions that were
in this paper what they did, they kind of reformulated some of the Poisson reduction theorems that were around in this graded picture. So there were some reduction theorems for Poisson structures before, but you had like some manifold with some involutive distribution and some compatibilities. And here what they understood is that you can actually interpret all the compatibilities that were required before very naturally in graded terms. So this is what I'm saying. It's just I'm extracting some. No, I will go. I will explain how this theorem comes out of the graded picture. So this theorem here comes out of doing some Marsden-Weinstein reduction in the graded setting, and then out of this Marsden-Weinstein reduction in the graded setting, you can extract this theorem. I will explain how it goes.
We shouldn't be.
No. It's just like I just want to say that I just wrote here the theorem to say that if you start with some more general reduction data, something that is more general than the usual Hamiltonian setting, you can also produce other Poisson manifolds. And if you know that in the usual Hamiltonian setting you have this Kostant-Sternberg BRST thing, so you can. It's natural to ask if you consider this type of theorem to ask what's the algebraic structure behind the homological formulation of this thing. So I just wrote here to say, okay, there's this theorem, and I want to see what's the homological version of this. So I will go into the, like to explain how these things appear. So I just want to motivate somehow.
But just I want to understand if will I be lost in the rest of your talk if I don't understand?
No. I will. It will appear again. This slide will appear again. I will write it again in I don't know, maybe in 3 or 4 slides. It will appear again. Okay, no worries. I just want to motivate what I'm trying to do. So it's just to say that you have some usual reduction setup, and then you have this more general thing. You know that this homological thing appears here. I want to understand what's the homological thing in this other picture here. But I will come back to, I will explain exactly how this thing appears. Okay, good. Okay, so I want to understand what's the corresponding homological version of it. So I want to understand what's the algebraic structure if you have the differential graded Poisson algebra in the usual Hamiltonian setting. I want to understand what appears here when you consider something more general. Okay, this is what I want to understand. Okay, so just like give you a brief view, maybe you already know it, but I just like to give you some idea of this, what's this BFV in degree 0 for this usual Hamiltonian setup. Okay, so you start with a Poisson manifold and a G action with an equivariant moment map. So it's the usual thing. So we have the Marsden-Weiss theorem, which says that you have this, when you take the constraints to manifold given by the 0 level set of the moment map and you quotient it by the action, you have a new Poisson manifold. So if we call like C, like the level set. So we have C red, just like the notation, C red would be the quotient. So we have that the functions on the quotient are the invariant functions on the constraints to manifold, right? So you have like, you take restriction and you take gauge invariance. Good. So if I denote by I the vanishing ideal of the constraints to manifold, so it's all the functions that vanish on this submanifold, this ideal is actually quasiotropic. It satisfies this condition. So it's closed under the Poisson bracket. And this comes from the fact that the moment map is a Poisson map. Okay, good. And well, using this ideal, you can actually see the functions on the constraints to manifold. So this restriction is actually taking the quotient by the ideal, like the usual thing when you have like this these ideals encoding some subvariety. And the interesting thing here is that you can actually model the invariant functions as this quotient that appears on the well, on the left-hand side for who is seeing the slides. So it's this normalizer quotiented by I. So this normalizer is a subset of the Poisson algebra that is so that when you take the Poisson, these are all the functions that when you take Poisson bracket of I, you are in I again. And you can prove that the functions that are invariant by the action on the constraints to manifold, you have always this identification between this normalizer and this invariant function. So in particular, you see that you can always talk about this normalizer quotiented by I. So somehow it's a way of talking about the functions on the reduced space without talking about the reduced space, right? So you don't need the quotient to exist to talk about this thing in particular, okay? So, and what I want to say, like you see, there are 2 steps here. One is restriction, the other one is taking gauge invariance. And the homological model, so to speak, for the Hamiltonian reduction comes out of realizing step 1 and 2 homologically in a certain sense. So for the first case, you take some resolution. And for the other case, you take like the Chevalier-Eilenberg, somehow the Chevalier-Eilenberg of a certain G module. And when you do that, you get this thing that I'm calling here, what's called Kostant-Sternberg BRC algebra, which is a differential graded Poisson algebra, denoting here by K. So you have, it looks like this. You take the Poisson algebra, the algebra of functions, and you have this wedge product. So the G part comes from taking the resolution, so this Koszul resolution, and G star part comes from taking the Chevalier-Eilenberg of this thing, okay? And you have a Poisson bracket because you have the Poisson structure on the manifold, so you have a Poisson bracket on this on the functions, And you get this super Poisson bracket by extending the duality between G and G star. So this is the so-called BFV bracket. Right? So you just extend the duality, as a derivation, so that it will be a derivation. So you have this algebra, and you have some differential that is actually an inner derivation that you construct out of the reduction data. So you have the moment map. So you can write this element here. And so the idea is that this differential should recover both the constraints and the gauge invariance. So it encodes all the information about the reduction. So here you have the components of the moment map, and the other part you have some Chevalier-Allenberg component of this. And this is so that this element satisfies this thing that's called master equation. So it squares to 0. Okay, so you have a differential graded Poisson algebra. And the theorem that appears in this paper by Kostant-Sternberg, and there's also like somehow more general setup, a paper by Stasheff, is that if you call, like I'm calling here I, the vanishing idea of this constraints to manifold, the theorem says that when you take cohomology of this algebra in degree 0, this is always isomorphic to the normalizer quotient by I. And this is always true. So it depends only on the regularity of the ideal. In particular, it doesn't depend on the fact that the quotient exists. But when the quotient exists, this is, we know, I said that this normalizer quotiented by I is the algebra function of the reduced space. So it's in this sense that that this construction produces a homological version or algebraic version of reduction. You have some algebra. When you take cohomology, this algebra gives you the algebra function of reduced space. But I want to concentrate on the fact that you have some structure on the level of cochains here, right? You have some differential graded structure on the level of cochains, and when you take homology, you have the algebra function of the reduced space. But there is some algebraic structure on the level of cochains, and I want to concentrate on that because this is somehow that's what's going to be generalized. So what's in the level of cochains. Okay.
Just curiosity, going back to the origins of the EFB, do you use terminology ghosts and NQ?
Yes.
Or generators of the
Yes.
G and G star?
Yes. I just don't remember which one is which, but so either G or G star should be the ghost, and the other one should be the anti-ghost. Yeah, I also have to I always have to double check to see which one is with the ghost and the anti-ghost.
So G generators of which G are the ghosts usually?
I think so,
But,
yeah.
The other ones are, I mean, it's maybe just a matter of terminology, but the proper analogy originally is anti-field. But I understand it doesn't quite fit.
Yeah. Or it's like it's like also the momenta, right? Associated to this ghost.
Okay, so yeah, it's the momentum.
Yeah, it's the momenta of this ghost that you read for taking the resolution. Yeah, I always have to double check to use the correct terminology. This is why I don't use it. Okay, so good. So this is I made my point regarding this construction. So I will come back to that slide and say that okay, I will explain exactly how this appears. This is what comes next. But just to say that there are more general Poisson reduction theorems, and it makes sense to ask what's the algebraic structure of the homological model or this type of reduction scheme. Okay, so there is something more general that I will explain how it appears and what are the features of this type of thing here. But it's reasonable to ask, okay, in the usual Hamiltonian setting, you have this differential graded Poisson algebra. So what happens if you try to do the same type of construction in this case? So what should appear? So should we get always a differential graded Poisson algebra, or should we get something more complicated? And well, as we are going to see, we get usually things that are more complicated. So this is I want to concentrate on the fact that I'm going to generalize the structure on the level of cochains. So what's like, just like to give some maybe some spoiler, is that in the usual Hamiltonian case, we have differential graded Poisson algebra. In this case here, what we are going to have in general is homotopy Poisson algebra. So in principle, you are going to get higher brackets on the level of cochains, but you have the same feature that when you take homology, you get the algebra function of the reduced space. But on the level of cochains, you have more things. You have more brackets. You cannot close, you cannot stop on the second one. Okay, so, and the way that I'm going to do the homological thing here is that I'm going to take the graded perspective. You see, because in principle, you don't know exactly how to proceed here. Like if you start with the non-graded data, it's kind of hard if you try to do the same thing that Kostant-Sternberg does here, because there are some decoupling between symmetry and constraints. I can explain better later. So it's not exactly clear how you should do the same construction that you do there. So what I'm going to do is that I'm going to do homological reduction of the graded thing, and I will do something there to get the homological version of this result here. So I'm going to take the graded approach. So somehow what I'm going to do is homological reduction of the graded thing. I'm going to do something there, and I'm going to get the homological version of this thing here.
Okay. I'm still a bit stuck on like how this Cattaneo-Zambon reduction was picture was exactly different from Mars and Weinstein.
Well, you see, well, the difference is first of all, the usual Marsden-Weinstein theorem. For instance, this equivariant map here, it takes value on the dual of a Lie algebra right away. It's like the dual of the Lie algebra that appears here.
So if you specialize that to...
You recover exactly the Marsden-Weinstein reduction. Not, you know, like this is one thing. And the other thing is that there is some compatibility here that I haven't explained yet what it is. So you say Hamiltonian action compatible with the Poisson bivector. So when you translate this compatibility, there's one more feature that is like in the usual Hamiltonian setting, you ask the bivector to be invariant with respect to the action. And in this case, the bivector is not necessarily invariant. So it's a particular case. The Marsden-Weinstein thing is a particular case of this thing here.
Yeah.
But this thing is more general in particular because you don't ask the bivector to be invariant.
Yeah.
So I will give some examples where it will be clear. Okay, so maybe examples from Poisson geometry, but examples. Okay, so like examples where you have exactly the lack of invariance of bivector controlled by some data. So, and I will come to it. Okay, so what I want to do, I'm going to do, now I will proceed to explain you more or less what's the Hamiltonian setup in the graded context. When?
When did they...
This paper is probably from 2008 or something. Yeah, from 2008. It's just like this. They actually reformulated as because there was some more general Poisson reduction theorems in the literature, but it was not so clear exactly what, you know, like people had the right compatibility conditions. So what they did in this paper was to interpret it very naturally in graded terms, saying, okay, so this kind of complicated Poisson reduction theorem here is actually pre-symplectic reduction, but actually pre-symplectic reduction of the graded thing. And then when you do that, you just extract this usual Poisson reduction theorem. It's just like looking at the results with a different from a different perspective somehow.
So there are also many natural examples. That is both for Cattaneo-Zambon case and Weinstein case.
Yeah, I will come to some examples where it's kind of interesting to look from this perspective. Okay, so I'm moving to the Hamiltonian. Okay. Let me see how good.
So
okay, let's see how it goes. Okay, so let me move. I will explain now the Hamiltonian reduction and how this thing here appears, this more general setup appears from the Hamiltonian reduction of the graded bundle, okay? So just like, maybe many of you already know about it, just like you want to maybe set some notation. So the shifted cotangent bundle here, I have a smooth manifold. I consider the shifted cotangent bundle for me is the graded manifold whose algebra functions are the multivector fields, are given by the algebra of multivector fields, okay? So you have like in local coordinates, you have like expressions of this. So you have these generators that are anti-commute. And you have like a Poisson bracket. So, and the Poisson bracket of degree -1. You see, when you take two multivectors of degree P and Q and the Poisson bracket, it lowers the degree by 1. And well, it's symplectic in a certain sense. So it has this type of expression here. So, but this bracket here is nothing more than extension of the bracket of vector fields to the algebra of multivector fields. So it's somehow something simple. But when you write this in coordinates, you see that it's symplectic. So it has this simplet face here. It's a graded version of the usual simplet Poisson bracket in the cotangent bundle, non-shifted. Okay, so this is the simplet manifold that I will be working with, the graded manifold that I will be working with. So what about the reduction of this type of thing? Okay, you have some simplet manifold with a graded structure there. You can try to mimic the usual Hamiltonian procedure for doing reduction for it. So what do we need? We need some graded algebra. So I hear it's concentrated degree 0 and -1. It's by degree reasons. Otherwise, you don't find the correct Hamiltonian functions. Okay, it just like takes some algebra, concentrated in degree 0 and -1, acting on this graded manifold. So you just have a Lie algebra map from this graded algebra to the algebra derivations, but now derivations of the graded algebra. Okay, so derivations of these multivector fields. So you can call like vector fields on this graded manifold. So derivations of this thing. So it looks complicated, but maybe it's strange, not complicated, but it's strange. But the point is that I want to define the notion of moment map. And it makes it much more geometric once you have the idea of a moment map is. So a moment map is a morphism. I'm calling here oddly algebras because I shifted the algebra there. But what's a moment map? Like in the usual case, a moment map is the assignment of a Hamiltonian function for each one of the infinitesimal symmetries, right? So it's a function when you take the Poisson bracket with it, it's a symmetry. So I'm doing the same thing here. So I take for this U, which is something that will be a derivation of degree 0. I assign a Hamiltonian function, but it's a Hamiltonian function that is actually a vector field because this bracket has degree -1. So this Hamiltonian function here has to be a vector field. And in this case, this derivation will be a derivation of degree -1, and this bracket has degree -1. So this thing here has to be a function. So the moment map is just the assignment of some vector fields and some functions. So and each one of these vector fields and functions are Hamiltonian functions for this symmetry, for these infinitesimal symmetries. Okay.
So, just unwrapping by degree.
Yes, exactly. So
and just
this thing here is something that is a derivation of degree 0.
Yeah.
So because I asked this infinitesimal, this graded algebra, this morphism from G to the derivations to be preserved degree. So what I'm doing here is just assigning a Hamiltonian function for it. But I know that this bracket is a bracket of degree -1. So I just say I need this to be a vector field, but a usual vector field on the manifold. And similarly, the other thing will be just a function. And there are some, but I also asked this thing to preserve bracket, to preserve the bracket. So there are some relations between these vector fields and these functions. They are not arbitrary.
But just wondering, what is special about taking the algebra that's concentrated in degree 0 and -1?
Yeah, it's related to the fact, it's related to the degree of the bracket somehow, because it can be strange to find the correct Hamiltonian since this bracket has degree -1. Maybe I think that it will be somehow degenerated in certain sense.
So if you just take some arbitrary graded the algebra with components in other degrees, it'd just be too complicated.
Yeah, I think so. Yeah,
Okay.
I think so. Yeah, I think so. But I was asked this question another time, but I never remember exactly what I said. So, but I think that it has to do with the fact that you want to find some Hamiltonians in a reasonable way, and the bracket itself has degree -1. So if you go the degree is too low, you don't find the correct Hamiltonians, and also you want the fact. Another thing is that you also want, it's good for giving a certain geometric interpretation for what appears here, that the ideal is homogeneously generating degree 0 and 1. Because if you take something, if you take a Lie algebra that has some component in degree -2, the Hamiltonian thing would have what degree? I don't know. You have to go positive degree. Okay, but we can talk about it later. But okay, so it's good to have some ideal that is homogeneous generating degree 0, 1 to give the correct geometric interpretation. Okay, cool. So, and there is some, there's a way of interpreting this dually by saying that the moment map is a map between graded manifolds. Just, you can define a moment map as a map from the Lie algebra to the Poisson algebra, and dually you can see from a map from the manifold to the dual. I'm just like not really important for what I'm going to say here, just because I'm going to use this notation to talk about like the constraints to manifold. But the constraints to manifold are entirely defined in terms of the constraints. By constraints, I mean the vector fields and the functions that I wrote there. Okay. So, okay, the constraints to manifold. So I'm using the notation. You see, it's the pre-image, somehow the pre-image of 0, but it's entirely given in terms of the constraints. So you have some functions and you have some vector fields, and you generate this ideal inside multivector fields. So you have this homogeneous ideal generated inside the multivector fields. And the fact, as in the non-graded case, the fact that the moment this thing here preserves the Poisson bracket, so the ideal, the map J sharp preserves the brackets, makes this ideal quasotropic. So you have some involutivity property with respect to the ideal. And you see here, you already see here how from this graded action and this moment map, you get some G action. So the G action is given by these vectors. And this map is actually given by this function, these functions, somehow dually, right? You can use this J sharp to define this equivariant map. So you see how there's actually, this is one-to-one correspondence. Out of this, you can produce this, and out of this, you can produce this. So you already see how there's some non-graded geometric data encoded here. So you can go back and forth. So, and geometrically on M, the fact that this ideal is quasotropic, you can actually see that what you have is you have some submanifold C that I'm calling G -1. So you have some constraints to manifold, and the involutivity property of these ideals, this ideal shows that you actually have some distribution here that is given by these vector fields, and it's actually tangent and involutive because of this property here. So you already see, how you started from something that's entirely graded geometric. It's just like the simple analogy between what's Hamiltonian reduction in non-graded case and to the graded case. But out of this, you got some very concrete geometric data in the non-graded manifold. But it's all encoded in graded geometric language in this ideal here. So, and you see, like, this is pretty much what you want to consider as reduction data for a Poisson manifold. Have some constraint, and you have some distribution, you want to take the quotient, right? Okay, good. So you have this tangent evolutive distribution in this level set. Good. Great. So what about the reduced space? So you have some action, have some constraints to manifold, and you can look at the reduced space. So here I'm describing here the algebra functions of the reduced space because it's easier in this way. And it's given again, you had normalizer, but now it's normalizer inside multivector fields. It's normalizer with respect to this Scalten bracket, which is this graded Poisson bracket. And the same thing works. So when the reduced space exists, the algebra function of the reduced space is given by this normalizer quotiented by J. It's just like direct knowledge. So one theorem that appears in this paper by Cattaneo-Zambon is this degree 1 version of the Marsden-Weinstein theorem. So it's a theorem about the reduction of multivector fields in a certain sense. So what the theorem says, so you have this moment map for the infinitesimal action, you have some regularity condition here. Let's say that assume that J is a regular value of this moment map and the action integrates to a free and proper action. But this is just so that you have some leaf space, right? So it's just that the conditions there are just for this submanifold to be embedded submanifold, and this action, so and the condition is so that you can take the quotient of the submanifold by this distribution. Okay, and what they proved is so this is like what I said, regular incompatible. Okay, so then when they reduce the graded reduced space associated to this data is just the shifted cotangent bundle of this leaf space. So you just take when you do the graded reduction, the graded reduced space is the shifted cotangent bundle of this leaf space. You see. So you extract this geometric non-graded geometric data, you take the leaf space, and then you take the shifted cotangent bundle, and this is the graded reduced space. Okay. So this is but this is reduction of the. You see, there are no Poisson structures here. This is reduction of the graded structure. It's reduction of multivector fields. It's reduction of the Schalten bracket, of the graded simplex structure. Okay. So, but Poisson, what's a Poisson structure? A Poisson structure is just a function, a special function of these graded manifolds. So I can try to couple this with a Poisson structure. Okay. And this is what I'm going to do now. So a Poisson structure is a bivector that satisfies its properties, a degree 2 function there, right? But you know this, right? You know this description of the algebra functions of the reduced space, okay? So I will say that a Poisson structure, something that lives here, on the non-graded manifold, is reducible if it's in the if it lies in the normalizer. So it's projectable somehow, okay? Because then you can just go through this isomorphism and take like the reduced Poisson structure on this leaf space here. It makes sense to talk about the reduced Poisson structure, the sense, right? Cool. So, and in this case, we have a reduced Poisson structure in the quotient, but notice that there is some flexibility here.
Can I ask just condition that the Poisson bivector belongs to this normalizer? Is it equivalent to the ideal being, I guess, the 0 degree part of that ideal being isotropic?
No. Because this condition here, you have some generators, right? So you can, in particular, take the derivative of the bivector with respect to this vector field. This is what I mean, that you don't need the bivector to be right away invariant. So when it's in this normalizer, this can be just in J. It doesn't need to be directly 0.
Okay. But how do you the classical reduction will be a special case of
yes,
right? So
yes.
how do you compare this condition to the usual condition that the generators of the ideal J are closed under the Poisson brackets they're generated by pi?
Okay.
How would that special case come out of this? Okay. That's not good.
Okay, yeah. In this special case, the usual case, what happens is that you can consider you have generators in degree. You have the generators in degree 0 that are given by the usual moment map and the infinitesimal symmetry. But there is some tie between them. There is some tie. So, and actually, to recover from the graded picture, you have to take the action of a special Lie algebra. The usual case is recovered from this graded picture. There is some thing here. You have to take the action of this differential graded algebra that is given in this way. So you take a map from here. You start from the beginning asking. You start from the beginning asking that this map is a map of differential graded algebras then you recover exactly the picture before. Because then there's some relation, you are going to get that this thing is invariant and all this stuff. So, but here I'm somehow getting something more general because I didn't start with, you know, you see from the beginning, I didn't specialize what's the relation between pi and the constraints. So there is a way of specializing what's the relation between pi and the constraints, and to recover the usual case, one way is doing that. I'm going to come to actions of the GLAs in a moment, and I'm going to try to explain how it goes. But because in the beginning, you know, you see, I just see how I formulated the Hamiltonian picture for the graded reduction. I just ask a map from a graded algebra to this algebra. And there was no Poisson structure around at all. So there is no way that I can tell what's the relation between the constraints and, you know, you had to tie somehow the Poisson structure and the constraints. And one way of doing that is taking action, the action by the GLA, and asking right away, since the beginning, you are going to have something here, and then this is going to tie everything. I will come to that. Okay, but in principle, you know, you have some flexibility of how this Poisson structure interacts with the vector fields and the functions. So this is what I'm going to point out here. And like there's some paper, by some papers by these two physicists called Yakovich and Sharapov, where they call it weak Poisson structure, right? So it's a Poisson structure that have this property that lies the Skouting bracket of it with itself. It vanishes upon some quotient, okay, which is like quotient by J. And in Poisson geometry, I'm going to, if I manage time, there is a more concrete setup that's called Poisson, quasi-Poisson spaces, which are, you have a manifold with a bivector, and it's acted upon a certain object that controls the lack of invariance and the lack of integrability of the bivector. So it's acted by these quasi-Lie algebras.
But just to be precise, these weak Poisson structures of Yakovich, are they the same as?
Yes.
Okay.
Yes.
Okay, then
Yes. Yes. So they define it in the context of what they call generic gauge systems, which are exactly this submanifold with this evolutive distribution, but you know, like in their language. So you have to extract it somehow, but it's the same. It's the same. Okay, cool. So, you know, there's a way of tying the Poisson structure with this construction. Okay. You see, the non-graded perspective. So in non-graded terms, when you translate what's this condition, you get some, what's written here. So you have this infinite of mg invariance is like you consider functions that are defined on the manifold, but functions that restrict to invariant functions here. So one thing, this condition here says that these functions that restrict to gauge invariant functions on C, this is a Poisson algebra. This is one thing. And the other thing, well, is this pi sharp of the annihilator of the tangent, whatever. This is contained in this distribution here. So in the usual case, this is the usual Hamiltonian case, this is usually an inequality. So in this case here, somehow you are quotient out by something bigger than that you would quotient in the usual case. So the distribution that you are going to take, the quotient contains this thing, but in the usual case, this is the equality. So somehow you are, in this case, you are allowing yourself to quotient more directions in a certain sense. And this is actually comes with the fact when you take the action by a DGLA and this is the DGLA, this thing here will make this to be an inequality. It has to do with this Mac being surjective or whatever. Okay, but doesn't matter, it just comes. Okay, so there's a way of translating non-graded terms, this thing. And then you know everything. You know, like the graded Marsden-Weinstein reduction theorem. You know how to relate this geometric data to Poisson structures. And now, out of this graded Marsden-Weiss theorem, you just extract this theorem by Cattaneo-Zambon, going through this path, right? You do graded reduction. You know that there is some flexibility to the reducibility of this special degree 2 function, which are these two conditions that I wrote here. You know that there is a certain reduced space, and then you get this kind of generalized Marsden-Weiss theorem going through this path, right? You see? Now is it clear or not? Maybe.
Please continue.
Okay. But there is some, you go to the graded picture, you do something there, but you know that the Poisson structure is still around, and you just have to read some relation between the graded picture. You just have to try to read what's the precise relation between the Poisson structure and what you did in the graded. But the main thing is that there is this geometric thing here behind what you are doing in the graded setting. There is this submanifold and this distribution. And when you do graded reduction, you have this multi-vector field and so on. But in the end, you have this leaf space over there, and this Poisson structure goes down to this leaf space. So, things. Cool. And then the homological version of this result, to get it, I'm going to do homological reduction, but I will how did I get this result here? I did like graded reduction, Hamiltonian reduction. I did something, and I got this result. To get the homological version of this thing, I will go again to the graded picture. I will do something there, and I will try to couple it with the Poisson structure. So the first thing is to do homological reduction of multi-vector fields. And then afterwards, I try to couple this with a Poisson structure. Okay, so the path is more or less the same. Okay, so time-wise, I'm going bad, but let's see how it goes. Okay. Okay, so something that I'm calling here BFV in degree 1. So it's BFV for doing reduction of multi-vector fields. Okay, so start with the graded Hamiltonian reduction data. I have this moment map, so which prescribes this vector field, these functions. And there's one important thing here. If you go back to the thing that I said in the beginning, the construction of this BRST algebra, notice that you can see this BRST algebra as the algebra of functions of this special graded manifold here. You take M, you take the product with this cotangent bundle here. So you see this dual in degree 1, you take the cotangent of this, and you take product with M. So it gives you these generators in degree 1 and -1. And then you can see this thing here as the algebra of functions on this graded manifold. And the BRST differential is a homological vector field in this graded manifold. Okay, so I will this perspective here is important because it makes it easier to do the analogous thing here. So what you do is really the analogous. You take your graded manifold and you extend it by this shifted cotangent bundle now. But now the graded algebra. You have here, you shift it by 1, and you take the shifted cotangent bundle of this graded algebra. Well, it produces something kind of strange, but the point is that you have, instead of having that wedge product here, you have the symmetric algebras, graded symmetric algebras. But see, here you had only 1 degree, which was because these algebras are not graded. So here you only have the degree that is given by the exterior powers here. But here you have internal degrees because this thing here is graded and this thing here is graded as well. So you have 2 degrees. You have the degrees that is given, the degree that is given by the symmetric algebras, but you also have internal degree, which is somehow polynomial degree in these graded variables. Okay. So, and there is a Poisson, this thing here, so that the duality between one element and corresponding dual is of degree -1. So this is why I took this in this way. And then I can do the same thing. I just extend this to be Poisson bracket in this whole algebra. Okay. So as I said, there are 2 degrees. So you have the degree given by the symmetric algebras, but you have internal degree as well. So, okay, so you define this algebra, you define AN to be the difference. You have a degree that is the difference between the symmetric algebras. And it's bigraded. So you have the degree, this degree, but you also have the internal degree, or what I'm calling function degree. So, and the degree, the difference between this symmetric algebra here and this one here is what I'm calling total Gauss number. So I'm, like just counting how many duals and non-duals you have. But you also have the function degree with polynomial degree. It takes into account the internal degree, each one of the graded generators. Okay. And this is what this will be. So these are the algebra functions of this n with this BFV bracket with this total Gauss number is the algebra will be the underlying algebra of the thing that I will be doing. And you have some BRST charge for this case. So the BRST chart, what it should do, it should take into account the symmetries, the constraints, the constraints and the symmetries, right? And the expression is exactly the same. So you have the vector fields, you have the functions, and you have to complete here with some Chevalier-Allenberg, but it's now graded Chevalier-Allenberg. Okay. So this one is just like, because you have this graded algebra, you have this graded algebra. So the first part is the action of G on itself, but G act on H. So the second part is the action of G on H. Okay. And you see, and it has total Gauss number 1, and this internal degree is 1 as well. Okay. So because this is 0, this is 1, and so on. So you can just count the degrees. And well, it satisfies this property. It's just like equivalent to the Jacobi identity, but for the graded algebra. Okay. Cool. Cohomology, but now cohomology at total Gauss number 0. You have 2 degrees. Okay. And I know, well, this theorem appears in a very maybe general form in a paper by Bonek, Cabrera, and Zabzin. And it says that when you consider this algebra, this A, with the BRST charge, when you take homology at degree 0, you have isomorphism of degree -1 Poisson algebras. So this is homological reduction of multivector fields. So when you consider this BFV algebra of degree 1, you are doing homological reduction of multivector fields. See, I wrote here. So under the assumptions of the theorem that I told before, we know that this normalizer is isomorphic to multivector fields on this leaf space. So this thing here is really homological reduction of multivector fields. You have this homological model for doing reduction of multivector fields. Okay? Okay, but this is, again, reduction of the graded structure. There are no Poisson structures around yet, right? Let's try to couple this with a Poisson structure. So a Poisson structure, as I said, it's reducible if it lies in the normalizer, right? Because then you can just take, this thing here. So if the Poisson structure lies in the normalizer, it naturally descends. It defines for you a bivector in the quotient. So if you have a Poisson structure that is reducible, I wrote there, reducible with respect to the geometric data associated today, it means reducible with respect to this submanifold and this distribution. Okay, this is the geometric data associated today. Then, if it's reducible, you have a corresponding cohomology class. There, you can take it, right? Because you have this isomorphism. So if pi is reducible, you have something here. You just consider a corresponding cohomology class here. And this is this pi, capital Pi there. So what happens is that when you take now cohomology 0, 0 here, 0, 0, you can use this cohomology class to define a derived bracket. And this is a Poisson bracket. And moreover, this is the Poisson algebra of the reduced space. So this bivector descends, and you recover the Poisson algebra of this reduced space through this derived bracket construction. Okay. Okay, well, that's already some type of homological reduction for this picture. But as I said in the beginning, I want to focus on the level of cochains, right? I want to see, is there part of something bigger? Because, I have this Q, And then I take homology and I use pi to do something. But you can wonder if this is part of something bigger, right? And it is. So there is something that I'm calling extended BRST charge here. So you just start, you construct this extended BRST charge in the following way. You notice that Q, sorry, maybe it's better if I write here. You consider Q, oops, maybe right here. So you see that Q, both Q and pi are functions on this graded manifold A, right? For instance, you take a representative for the cohomology class associated to pi. There are functions. So you know that Q satisfies this equation, the master equation. You know that pi is a cocycle, right? But both functions, you can consider, okay, take this sum and you try to compute that. Is this 0? Well, in general, it's not. But under suitable regular conditions, you can complete this so that it satisfies this master equation now. But you have maybe now infinitely many terms. Okay. And then, well, the question is, what's the structure, associated to the extended BRST charge? Should it induce structure somewhere in this big manifold N? In this big manifold N that I'm considering, that is N tensor 1 G 1 dual. So should this extended BRST charge is a function here? What's the structure associated to this thing? Where does it induce a certain structure here? How it works? And actually, there is a certain Lagrangian there. So there is a special subalgebra of this algebra A that is given in this form. It's Lagrangian, it's abelian algebra with respect to this bracket. The bracket vanishes there. 0, identically 0. And this extended BRST charge induces a homotopy Poisson structure there through this derived bracket construction. So what I'm using here is this Voronov construction of homotopy Poisson algebras, or homotopy algebras, sorry. So you see that using this algebra, you can define a derived bracket that is in this way, and then you define a second bracket that is in this way. And then, so on, you define derived brackets given in terms of the higher terms. And the fact that this satisfies this equation here makes this a homotopy Poisson algebra, meaning that you have higher coherence conditions on all these brackets. So in particular, you have some Jacobi up to homotopy, but you also have you have other relations that are harder to interpret. But in particular, on lower degree, you have something that is Leibniz up to homotopy or Jacobi up to homotopy. And this is just what I wrote here. For instance, this is the next equation that will appear here when you try to solve this. So you add one term and you extract this first condition, and the condition that you get is something that is Leibniz up to homotopy. You see, you have some Leibniz rule here, and here there is some homotopy. So there is some differential, some three-area bracket, and so on. So this is really Leibniz up to homotopy. And you extract this out of this equation here. Okay. So the remark, interesting remark, is there is a datification. This is bi-graded. Upon the choice of this Lagrangian, in some papers, even papers by Alberto, this Lagrangian is called like polarization somehow. And upon the choice of this Lagrangian, you have a datification of this algebra with the algebra of multivector fields on this graded manifold. So somehow you have this N, big N, is the shifted cotangent bundle of this Lagrangian. So this thing here is somehow a graded version of the Weinstein-Lagrangian neighborhood theorem, but it's global somehow, right? And this is also related to recent work by Michael Cueca and Jonas Schnitzer, where they talk about this deformation of Lagrangians and so on. Okay? But what's interesting here is that, you see when you compute these degrees, the total degree is always 2. So this thing here, this S infinity, is a formal bivector in this Lagrangian. So this connects with, something that Cattaneo and Felder called P infinity structure, and it's something that is like the recent literature in this paper by these people that do like derived geometry. They call zero-shifted Poisson structure. Okay, so it's this formal bivector in this type of thing. So it's interesting that you have these structures. Somehow all these things are there, but it's right to grasp. It's right to. Okay. Cool. Okay, so this is one thing, and now then the theorem. Okay, so the theorem is that like we start with the generalized data. So you start with this generalized Hamiltonian setup that I explain how it appears from the graded thing and so on. And you assume some regularity compatibility conditions that is just for the existence of this Leaf space. And then this algebra, graded by total Gauss number, which is like this difference between the exterior powers in this case, admits a homotopy Poisson structure, so it has higher brackets, and the cohomology, but the cohomology still compute the algebra functions of the reduced space. So it's in this sense that this theorem generalized the previous theorem, because in the other theorem I only had I had a differential graded Poisson algebra. I had differential and two bracket, nothing more. Here, in principle, I'm getting higher brackets. So it's generalizing the structure on the level of cochains, but the statement in cohomology is still the same. Okay. So well, the proof is maybe it's kind of clear now. You just take the corresponding graded map associated to this. You consider the BFV in degree 1. You construct the extended BRST charge, derive brackets, and that's it. Okay, cool. So I have a couple of I have some examples, but maybe my time is running out.
Yes, that's time for example because that's my question. You're not to answer my question.
Okay. Okay. So give me 5 minutes. I can go through some two examples. I had maybe 4, but I go through. This one is kind of quick. Action by the DGLAs. Okay, which is what I said before. Now you start in this case here. We are going to couple since the beginning the symmetries and the Poisson structures, the Poisson structure that you consider in the manifold. So you have a DGLA, so you have a DGLA concentrated degree -1 is 0, but you also have the differential. And now you have a Poisson manifold, but now you ask this map to be a map of DGLAs. So there is some relation between this and this thing here. And what happens is that you get this type of condition when out of the fact that if you consider this map to be a map of the GLAs, you get these two conditions, these relations between the Poisson bivector and the constraints. So in particular, there's some, the constraints of degree 1, they are tied with the constraints of degree 0 through this equation. But this first equation here is also saying that in this case, the bivector is invariant. Okay, so you see that if you consider the DGLA to be the DGLA that I wrote before, this thing here being the identity, minus identity, whatever, then you recover exactly the usual conditions of the usual Hamiltonian context. The constraint, the symmetry is exactly the Hamiltonian vector field of constraints of degree 0. Okay. So in this case, you have the usual, you have the BRST charge as I wrote before, but you have the Poisson. You can write that pi very explicitly. And this Aij here is just like you just write the matrix of this delta. So you have H here, you have delta, you have some basis. V is a basis for H, and you have so you have some V's here, you have some U's here. So and this term here is just like this, writing this matrix A, the matrix of that map. And then actually, when you consider that this algebra here, this will be just like delta Ij, right? And this, when you do derived bracket, you see that you recover exactly the duality between the Kostant-Sternberg thing. It's just like it will be exactly the same bracket, right? So, well, it satisfies this property. And then this induces a differential graded Poisson algebra structure on this algebra here. So in particular, when you take H to be J, and this map delta to be the identity, you recover the usual thing. Okay. And the relation is also, the relation between the constraints is tied here on this thing. Okay. So this is one kind of theoretical example, but there are some more concrete somehow examples. So bialgebra actions. So you have a Poisson manifold and you have this object is called bialgebra that acts there. So maybe I don't have time to go through all the details, but the point is that you have some action, you have a bivector, and this F here is a certain cocycle for the action of the algebra on the the exterior power of G. But okay, doesn't matter. The important thing is there is something that acts, and the lack of invariance of the bivector. So this is the Lie derivative of the bivector with respect to the symmetry. It's controlled by this data here. So somehow this is saying that this bivector phi, it lies in the normalizer now. It lies in this J, but J now is just, I'm just considering this infinitesimal symmetries. It's just generating degree 1. And this condition here is saying that pi is in the normalizer of this graded ideal. The way that it's in this graded in the normalizer is controlled by this bialgebra data. It's entirely controlled in terms of this object that acts. Okay, and in this case, you see, I don't have constraints of degree 0 here. I only have constraints of degree 1. I don't have a restriction. I just a quotient right away. So I don't have that part that is like that is controlling the quotient. That is the G part. I only have the part that controls the symmetry. And then I have, like, you can write the extended charge. The charge is like this. You only have the constraints of degree 1. And you can write this guy, you also can write explicitly. And it's given entirely in terms of the bialgebra data somehow. You have pi, but you also have here the symmetries and the bialgebra data. A here is just the coefficients of this F. And, well, and just as I said, I'm not considering constraints of degree 0, but then you can write this proposition here. You can say that when you have a bialgebra action on this Poisson manifold, you have this algebra, and there's a homotopy Poisson structure here, where the first brackets are given like this. You have the usual Poisson bracket, but the bracket between the generator here and generator here is given by, you take derivative, and this bracket here is the bracket, because when you have a Lie bialgebra, you have a Lie bracket on the dual. And this is the bracket that appears here. Okay. And well, then this one is 0. But you can compute explicitly at least the first degrees of this bracket. But in principle, you have higher brackets. In this case as well. It doesn't close on the second one. You also have higher brackets. Okay, I have some other examples, but maybe time is over, so I don't want to. Okay, maybe just this one. This one is like, now you have something that's called bialgebra, a quasi-bialgebra action. And now you have, besides having the bialgebra, usual, the thing that you had before controlling the lack of invariance, you also have something controlling the lack of integrability. But it's also given, this is a trivector in the, in this context of this quasi-bialgebra. So this thing, the lack of integrability of the bivector is controlled by this trivector here. So it's again saying that, you see, it's one of these weak cases where pi is in J, right? But it's in J in a controlled way somehow. Okay, so in this case, I also don't have the restriction, I only have the action. And here you can write the first term. The first two terms are the same. And the third term, at least, the first part of it appears the other thing that you have here. So it's related. You can try to do some computations to see how this appears this term appears in the Jacobiator of the bracket induced by this one. And so, okay. So, okay, I finish here because the other things I don't have time. Okay, thank you.
Thank you very much. Yeah, very exciting talk here. Any question? No? You already answered. So if in the audience, I tend to see any question.
Okay, fine.
So
Can I ask another question?
Yeah, sure.
So you mentioned the P infinity or Poisson infinity algebras. I think in literature people have different notions of what exactly that means. Or what is the notion that you're referring to?
Well, the notion I have first, I consider that in principle I have just like you can consider you have an LA infinite algebra. This bracket they assemble together into a LA infinite algebra. Yeah, but you also have some derivation property related because you have an algebra, so you can multiply entries, and you have some derivation property. It's more than LA infinite algebra because you also have this derivation property. So in particular, you have that Leibniz up to homotopy that I showed, and all these things. So you have each entry, you have some derivation property for the bracket, but you have the LA infinity and you have something additional, which is this derivation property.
But the precise like algebraic structure, I think you mentioned it was described by Cattaneo and somebody.
There's this paper by Cattaneo and Felder. It's like they found this P infinity thing when they were doing something that they call relative formality. But it's like this paper is kind of old somehow already, like maybe not so old, but maybe 2005 or something. They did this the relative formality. And this concept appeared there, this concept of having some higher version of a Poisson algebra.
So I just wonder if you know how this is related to like this systematic way of constructing like infinity versions of algebraic structures. Like L infinity appears as an infinity version of E, A infinity is infinity version of associative algebra, and so on. Like, do you know whether that notion of P infinity is actually this general construction?
Well, I think
to Poisson algebra?
I think so. Yes. Yeah. I think that's definitely the right notion. Yes, because if you see when I talked about that there is identification of this algebra with the multivector fields on this graded manifold, you see that you are considering all these terms of this extended charge. They are bivectors on this graded manifold. So you have a formal bivector. So you have a bivector with higher terms. And when you take derived, because what you are doing here is somehow taking derived brackets with respect to this formal bivector. So in a Poisson bracket is a derived bracket, but it only of one bivector. It's pi. But in this case, we are considering this formal bivector, and you see that the master equation makes this thing coherent in a certain sense. So it makes everything fit together nicely into this L infinity.
Okay. So in that context, I know that there's some general homotopy transfer theorems for transferring these algebraic structures. So do you see your constructions as like examples of specific homotopy transfers?
Well, I don't know the answer, but yeah, someone asked me this question before. And I think because you see, I made some choice here when I wrote this extended charge. So I wrote Q and I took a representative of the cohomology class associated to pi, and each step of the construction of this extended charge, I have to make some choice somehow. And I think this is a question that we considered, but we haven't looked very much. We haven't, work a lot on it, but it's a question that we ask is like how this structure depends on these choices somehow, and we think that the right way of doing it is taking this homotopy transfer and comparing, but I don't know. Like I think that there is a way of using this homotopy transfer here, but for doing a different thing, not to see right away the structure as coming from the homotopy transfer or something. But what the idea that we had before was like that maybe to compare the structures, we should use homotopy transfer to transfer two different things and see that they are, okay, probably they are all quasi-isomorphic in a certain sense, but we just don't know exactly how to compare. So But
So I suspect that probably you are doing essentially kind of maybe by hand some version of this homotopy transfer.
but I don't know because what I'm
Yeah, but
doing.
So if you're doing something different, then it's already quite interesting. So
No,
it's
because
an
what-
important question to, like
Yeah,
you said, compare.
Yeah, sure. Because I try to see, maybe people that are really specialists in this business, they know it. Because what I do here to take this bracket, I'm using this Voronov construction. Like Voronov has this, you have this super Lie algebra, you have this abelian algebra with this derivation, and you induce bracket there. But someone asked me, okay, is this thing that we are doing homotopy transfer? Then I tried to look at Voronov's paper to see if it's because if someone knows about it, probably he is the person that knows about it. But there's no, I didn't find it, so I don't find the mention of homotopy transfer. Maybe there's somewhere there that maybe I didn't. I was not careful enough to look at it, but because what I'm doing is Voronov construction, right? So I don't know if this construction is related to homotopy transfer. Maybe he knows, but I don't know. So maybe, yeah.
Okay, if there are no more questions, let us thank speaker.
Thank you.